Hello, everyone, and welcome to physics on a fine Wednesday morning. What we're going to do today is just kind of talk about the agenda. And so, if we get right into that, just some friendly reminders for you guys. The book problems that were assigned on Monday are due today, and those are right here. The book problems are page 347, numbers 6 and 8, and then page 348, numbers 11 and 12. So please make sure you turn those into the correct hour hanging file in the basket, and everything will be good. Shortly after I'm done talking about the agenda, we're going to talk about some class problems today dealing with gas laws. And I do have one more pressure problem just to show you guys to get you ready for the quiz, which is later today. All right, so today there will be a quiz that will basically follow right after the class problems. On this quiz, you can only use a 3x5 index card, write whatever you want on it, front and back. You may not use notes or books or anyone sitting nearby you. After the quiz, there's a couple options on what you can do. One, you can finish up the lab from yesterday. I did clean the lab up, so if you need data, see if you can grab it from another group. But I didn't get any labs turned in yesterday, so you should probably have like graphs that you need to finish, questions that you need to answer, those types of things. Could definitely be done today after the quiz and then turned in. I'm asking that the lab be done by Friday. Okay, so try to get it turned in as soon as possible. The other thing that you could do is you could work on the extra credit problems that were given to you by the sub on Monday. There should be little tiny slips of paper that have the extra credit problems on them. It's basically a page in the book, and I want to say it's about 5 or 7 different problems that you can work and gain some extra points, and who doesn't like that? The other thing you could do is you could watch lesson 5. And lesson 5 is pages 354 through 357 in your book. So you can either read about it, or if you want to watch the lesson online, that's cool with me. A lot of you answered in the survey that you have smartphones or phones that are able to go on the internet. Why don't we put those babies to use and actually use them for something educational? So you could watch lesson 5. And it was brought to my attention that the school's Wi-Fi is blocking YouTube, which I guess is good, but a sort of a problem because that's where I host my videos. So if you go to my website, and here it is in all its glory, wow, what a beautiful thing it is. Instead of clicking physics video lessons, click video lessons that do not involve links to YouTube at school viewing. If you click that, I just have the chapter 13 videos here just because this is the chapter that I'm gone for. But basically, you can see all of the chapter 13 videos up on the screen. And basically, if you watch it through my website, oddly enough, the school's Wi-Fi does not block this, even though it's still hosted through YouTube, which is, I guess, kind of funny. So I'm asking you guys to take a look at this one, lesson 5. If you haven't watched the other lessons, I would encourage you to watch those just because, again, you're going to have to turn in your notes eventually, and that's something that is worth a grade. Okay, so check out lesson 5, please. Okay, let's get right into the class problem. So hopefully you've had these passed out to you, and we can just work some problems here to get you warmed up for the up-and-coming quiz. Let me just change my pen color to something that is actually visible. How about a little bit of cyan action here? Okay, so problem 1 says a bubble with a volume of 1.2 centimeters cubed is released underwater. As it rises to the surface, the temperature of the bubble increases from 27 degrees Celsius to 54 degrees Celsius, and its pressure is cut to 1/3 of its initial value. What is the volume of the bubble at the surface? Okay, so what I recommend doing with problems like this is I start to write my data like before the change happened and then after the change happened. So before the change happened was basically this bubble, like if I draw like the ground here and like, I don't know, here's like a vent and here's the bubble. Before it climbs to the surface, what do we know about this bubble? Well, one, its volume, I'm going to call this volume 1, V1, is 120 centimeters cubed. Okay. As it rises to the surface, the temperature increases. So I'm going to call this first temperature, right here, 27 degrees, I'm going to call that T1, its temperature increases to 27 degrees Celsius. And then it goes to 54, and its pressure is cut to 1/3 of its initial value. Okay, so we don't really actually know the official pressure, but we can just give it an arbitrary term. So I'm going to call pressure 1 just 1, okay, because 1's really an easy number to use. So we're going to call it just 1. So now that's one side of my chart. Over here on the second side, this is like the after effect. Once the bubble gets to the surface up here, what do we know about it? Well, the volume, or V2, would be our question, right? That's like what we want to find out. What is the volume of this bubble? The temperature, we'll call T2. The temperature is now 54 degrees Celsius. And the pressure has been cut, so we'll call it P2, to 1/3 of its initial value. So it was 1 over here. It is 1/3 of its initial value over here. Anyway, now, what equation do I want to use? Well, there's this thing called the ideal gas law. And basically, it goes something like this, where you have P1 over V1 over T1 equals P2 over V2, times V2 over T2. Okay? And basically, if you just plug numbers into this equation, so it looks something like this. My pressure is 1. Because I just said it's 1. I made up a number. I mean, you can make it 10 if you want, but then you have to cut that into 1/3. The volume is 1.2 centimeters cubed. 1.2 centimeters cubed. And the temperature was, let's see here, 27 degrees Celsius. Now, before I write this temperature down, those of you who have watched videos have known that I've said you need to convert this to Kelvin. And so 27 degrees Celsius would be 300 Kelvin. So we actually put that down here, okay? And the reason why is these gas laws don't work when you start putting negative numbers in it. It just gets really funky. So since there's no negative numbers in Kelvin, that's why we like Kelvin. Okay. Over here, we have P2, which is, P2, which is 1/3, okay, 1/3, times V2, which is what we want to know, divided by this temperature, which is 54 degrees Celsius, but remember, we don't like Celsius, so we're going to convert that into Kelvin. 327 Kelvin. So that's going to go down here, 27 Kelvin. Okay, and basically, now you're left with some algebra to work with, and if you do the math, you get a volume, a V2, of 3.9 centimeters cubed. All right. And that would be the answer, right? And this is basically how the types of problems I would ask with the ideal gas law is just kind of plugging things in and then figuring out either a volume, a pressure, or a temperature, okay? So that's one example of a problem, okay? Let's do another one. Class problem number 2 says a cubic meter of carbon dioxide gas at room temperature, or 300 Kelvin, and at atmospheric pressure, 101,325 pascals, is compressed into a volume of 0.1 meters cubed and held at a temperature of 260 Kelvin. What is the pressure of the compressed carbon dioxide? All right, just for fun, so you guys don't get bored, and not that you could ever get bored when I would talk to you, I'm going to change this color to yellow. That is exciting. So, first things first, I recommend, let's see, what do we have here? Just gas, right? So gas is kind of hard to draw, but I recommend having like a before and after chart here of comparing the pressure, the volume, and the temperature, okay? So it says that carbon dioxide gas at room temperature, okay, so I'm going to call that T1. T1 is 300 Kelvin. And atmospheric pressure, so I'm going to call this P1, atmospheric pressure is 101,325 pascals, is compressed into a volume, so it calls V1, of 0.1 meters cubed. Oops, let's see here. I already goofed up. You guys should be yelling at me. What is this? It's a cubic meter of carbon dioxide gas. This is the after, and so even I make mistakes, which I guess isn't that surprising. So it's a cubic meter. I apologize. V1 is a cubic meter. On the other side, like the after effect, it says it is compressed into a volume of 0.1 meters cubed. So that would actually be my V2, 0.1 meters cubed. And it's held at a temperature, T2, of 260 Kelvin. I want to know what is P2. And notice how I've kind of like lined things up, like my temperatures, my pressures, my volumes. You don't have to do that if you don't want to, but it just, to me, makes it maybe a little bit easier to read. So I'm going to use the ideal gas law here. P1 times V1 over T1 equals P2 times V2 over T2. Okay, and basically, if I just start plugging my numbers in, so I have 101, 325 pascals for my pressure, times a volume of 1 meter cubed, divided by a temperature of 300 Kelvin, equals pressure, which I don't know, a volume, which is 0.1 meters cubed, divided by a temperature of 260 Kelvin. Okay? And basically, if again, working the math, doing a little bit of algebra, you should get a P2 of, drumroll, 878, that's supposed to be an 8, 878,000 pascals, PA. Okay? And then my answer. Okay? Cool beans? I hope so. All right, that's the 2 class problems I passed out to you. Now, you guys are in for a special treat. I have a bonus class problem that was not written down for you guys. So this is just, if you want to write this down, you certainly can. But just because of the issues with people struggling with pressure problems, I thought I'd give you one more just to, again, get you ready for this test. Let's see here. Let's use red. It sounds intimidating. Okay, so it says a unicycle has a mass of 65 kilograms. I don't know if you can ride a unicycle. I can't. But here's a unicycle, okay? And this guy has a mass of 65 kilograms, okay? And a clown, oh boy, with a mass of 70 kilograms is riding the unicycle. Okay, so that's supposed to be a clown. Okay, and he has a mass of 70 kilograms. Okay, this clown has no arms. There we go. The gauge pressure on the tire, the pressure in this tire is 1.7 times 10 to the 5th pascals. What is the total area of contact between the tire and the ground? Okay, so here's the ground. I'm wondering how much of this tire right there is in contact with the ground. Okay, and so our formula is P equals F over A. Pressure equals force divided by area. Okay. The big key is for this problem is we're trying to solve for A, right? We want to know what that is, and our pressure is given to us. It's right there. Okay, it's just sitting there. The big key to solving this problem is finding this F, this force. It's going to be the mass of the unicycle and the mass of the clown. Okay, because they're both on this unicycle, or well, the unicycle's there, but the clown is on top of the unicycle. We have to add these masses. So 70 plus 65 is going to be 135 kilograms. And remember, that is not the force, because mass is not a force, but weight is. And weight equals mass times gravity. So I have to take 135 times 9.8 meters per second squared. And if you work that out, I get a force of 1,323 newtons. Okay, that's my force, also known as my weight. Now that is not my answer, okay? I am going to plug that into F, this number in F, and then this pressure into P, okay? And I'm gonna try to solve for A. And basically it'll look something like this: 1.7 times 10 to the 5th pascals equals a force of 1,323 newtons over A. And basically, if you do a little bit of algebra and manipulate that to be able to get A by itself, you get an area, a very small area, of 0.008 meters squared. Okay, I rounded. It was like 0.0077 or something like that. So I rounded that up to 0.008 meters squared. All right. So that's the last of the class problems. I wish you guys luck on the quiz today. And once done with the quiz, make sure you use your time wisely and take care of some other business. I will see you guys tomorrow.